Hello, good evening. I am Abhinav Chandrakar. I am the TA for this course, Strength of Materials, which is being taught by Professor K. Ramesh. And today will be an extra session, and this is also the last session of this course. So we'll discuss today on some uh, questions from the current assignment. So on the discussion forum, some questions had been posted, which are mostly from between week 1 and week 5 assignments. So we look at those questions. If there are some additional doubts, we can address them too in this session. Hi Vishal, you are there, right? So if you have any doubts or any questions also from assignment, you can unmute and let me know. For now, let's wait for 4 to 5 minutes in case some others also want to join. Then we'll start with discussing like solving all those questions which were posted on the discussion forum. Archita has already covered the doubts from week 6 to week 12. Only one question is remaining in that week, like in those 6 to 12 weeks. I'll be covering the doubts from week 1 to week 5. Hmm. So in this session, I'll be solving all of those questions and the solutions which we make in this session, they will be uploaded in the resource folder in the shared drive. In the meanwhile, Vishal, are you there? In case you have any doubts you would want to discuss in this session, you can let me know. Uh, are you saying anything? I could not hear actually. So let me just quickly show what are the questions which we'll be looking at today. Mm,
Yeah.
so in the discussion forum, Mr. Bhagat had shared these questions week 1 to week 5. We'll be solving all of these today. I hope my screen is visible. Let's start now. So I'll not show exactly what the questions are because I can show only one screen at a time. So that will be difficult. But I'll just write down the question numbers as well as the mm, assignment numbers as well as the question number. So you can look up what the question is on your own screen or on your own device. Let's start with the last weeks and we'll then move on in opposite order. From week 5, we'll start and go to week 1. So the first question is from week 11, question 20. So week 11, question 20. It is as follows. We have been so it's the question is as follows. we have been given the stress state at a point. It's a 3D stress state, and we have to tell whether the material will yield or not, considering firstly von Mises criteria. Question 20 is asking for von Mises criteria. 21 is asking for Tresca criteria. So let's look at the 20th one. So here, if we try to make a stress tensor at that point, then you have sigma xx. Uh, Sigma xx is the stress on plane x along direction x. So normal stress in the direction x on plane x. So it is 100 megapascal. So this is an MPa. Sigma yy is 150 minus 150 megapascal. Sigma zz is 0. It's not, there's no stress. Sigma xy is normal stress in y direction, sorry, shear stress in y direction on x plane. So it is 25 megapascal, same as sigma yx. Sigma xz is on z plane x direction, there is no stress, so it's 0. Sigma xy, similarly, it's 15 megapascals. So this is our stress tensor. We want to know whether it will yield or not. So we need to firstly, to be able to apply von Mises criteria, we need to know the principal stresses. And there is a formula we have for knowing the principal stresses, right? So basically, you need to find the solution to your stress tensor. Let me denote it by this minus mm, sigma into I equal to 0. No, no, not equal to 0. So mm, let's, yes, what I was saying, you have um, to be able to get the principal stresses from this. You need to make this matrix of 100 minus sigma. Let me make it bigger. Yeah. And this should be the determinant for this should be equal to 0. So this is basically your sigma minus sigma I determinant equal to 0. And the values of sigma that you get from this will be the eigenvalues, and they are also the principal stresses. We have already seen this. So this is the way to find eigenvalues. You will get a cubic equation. From this, you will get a cubic equation. You will have to solve that equation. Yeah. Is there any doubt? Your
No,
voice
sir.
is breaking, Vishal. Okay. No, no doubts. No. So let me quickly go to what that equation is. Won't solve it directly here. So it is sigma cube minus sigma square into sigma xx plus sigma yy sigma zz.
Sir,
So
I have
this is
solved
a
this question 20 number
you have
and I am
already
not
solved
getting
it.
the value.
You are not getting
The right value, sir.
the right value. Oh, okay, okay. Actually, I tried it today. I was able to get the at least my principal stresses and strains were matching. I didn't
Sir,
calculate the
same
von
sir. My
Mises
stresses
stress.
are matching. All
Okay,
answer are
principal
matching
stress
except question
strains,
number 20.
principal stresses are matching for you.
Yes, sir.
Okay, so what I'll do, I'll just skip this part calculation of principal stresses. Let's directly calculate the von Mises yield criteria value. Hmm. Okay. So Vishal, is it you who had posted those questions in the discussion forum? And sigma yz square. Okay, so I'll not solve this. I actually know what the values are approximately. So I'll directly use them and then we'll put it in one Mises criteria and see what the values come. So sigma 1 is about I think 102.5 megapascal. Or 2 is hmm, so Vishal, your answer is not matching, you are saying. What is the answer you are getting? Can you tell?
Sir, 2.18 factor
Oh,
of safety.
okay. Okay, I see. Let's see. Hmm. Do you have it? Are these stress values which you are getting exactly the same?
Yes, sir.
Okay. So let's see what is one Mises criteria. I think it is sigma 1 minus sigma 2 whole square. You sum this. This should be less than equal to your 2 sigma square ys. Right? Is this correct?
Sir, I have used a different formula for factor of safety.
Uh, okay. This is
It is
for get
Fy.
okay.
Sir, it is Fy divided by root under sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square divided by 2.
divided by 2.
So
Okay, huh.
the standard formula.
Okay, okay. I see. So here we have been given the sigma ys value. Let's see. I think your formula is also right. Just a different way of approaching. 345 megapascal. And we know uh, factor of safety we have to find out. So let's just try to see what is the distortion energy we are getting using von Mises formula. So it will be sigma this. Let's and in the critical case it will be equal to sigma ys, but we also have to take into account factor of safety. So this value should be actually sigma ys divided by the factor of safety, right? F factor of safety, which implies your factor of safety will be equal to sigma ys divided by the, actually this will be this is not uh, there's a small issue here. This is not sigma ys by fos. So this will be 2 times this whole square. Yeah. So now you understood this. It should be 2 into sigma ys
Yes,
by
sir.
fos whole square, because this is the uh, new sigma ys that we'll be assuming, and we'll equate our distortion energy to 2 into sigma ys dash whole square. So we want to have a reduced yield strength which we'll compare with, just so that it will be like you will be incorporating factor of safety, so the chances of failure will be much lesser if we are using a smaller ys. So if we use this equation, then we'll get fos equal to sigma ys divided by sum of the strain stress components whole square. But we'll have to take a square root of this, I think. We'll have to divide this by 2. Yeah, yeah. And take a square root. Hello. Hi, Vishal. You are there?
Yes, sir.
Actually, my laptop suddenly stopped. So I'll just use it on my tablet. You can still see my screen.
Yes, sir.
You understood this formula, no? Which I wrote for FOS.
Yes, sir.
So basically, we are using this reduced value of sigma ys by dividing by FOS, and then using the same von Mises criteria. So here, if we do this calculation, Do you have the value which you calculated for this sum of sigma 1 minus sigma 2 whole square? Let's just do it again. Let's see. Sigma 1 my Vishal, did you also use a similar formula or you used? I think the one you told was different, right? You did not
No,
take
sir, it
into
was same formula.
this one only.
So we have to do then in the place of sigma 1 minus sigma 2, we have to do all the three. Sigma 1 minus sigma 2 square plus sigma 2 minus sigma 3 square. There is sigma in their formula. If we
Oh.
expand,
Hmm. Okay.
sir, have you solved this, sir? Have you solved this
I
question?
I had actually calculated principal stresses. I did not check the one myself. Now I am just adding it up. I'm doing the calculation.
Okay, sir.
Let's see whether it matches or not. Let's see. So I'm getting it like this. Root of what I'm getting is 345 divided by 223.7. So this will become MPa 345 divided by 223.7, 1.54. Is this the answer? Uh, yeah, yeah. So I'm getting the correct answer only. Vishal, you are there?
Yes, sir.
Uh, so can you just check if this was the equation you used? Maybe you used some different one for your calculations. Or I'll
Sir,
just
I used
explain
the
if
same
you.
equation, but I got 2.18.
Okay.
I think I have done I might have done wrong in using calculator.
Calculation issue might be there. Yeah. I'll quickly just write clearly what the formula I'm using is. Then maybe you can later check your calculation again.
Okay, sir.
My laptop is on again. It it had crashed.
Sir, my question
Okay.
is while finding the sir three values of that equation, characteristic equation,
Yes. Yeah.
three
Yeah.
principal trace, how I
Hmm.
will do this in exam hall because there is
In
no calculator.
so are you allowed to take scientific calculator
No, sir.
for your
Only
NPTEL exam?
no, sir. Only TCS calculator.
Okay. Oh, the simple one, no? Okay.
Yes, sir.
So this actually this equation cannot be solved directly by hand. I also tried a bit. Then I had to use some online computational like scientific calculator only. I think they won't give this kind of equation if they do not provide calculator. They'll give you a simpler cubic equation which you can just input some rand like guesses and find out the roots of that equation. Then you can do your calculations. Mostly they will not give you this kind of difficult cubic equation. So let me just simplify what I did. I directly wrote the equation here, no? So maybe some others might find it confusing. So what I did was here, here you have sigma 1 minus sigma 2. This is your usual uh, yield criteria for one mices 2 into sigma y square. If this is satisfied, that means it's at the edge of the yield surface. If the value of your sigma of sum of sigma 1 minus sigma 2 whole square is more than this, then it will yield. But here what we want is instead of sigma ys, we have sigma ys dash, which is equal to, it's a reduced value of yield strength we use, and it will be reduced by the factor of safety. And then once we put this value of sigma ys, then we'll just do the calculations. That was all. So if this is fine, I'll go to the next question.
Yes, sir.
Next question is week 8, question 8. Vishal, you only had asked these questions, is it?
Yes, sir.
Okay, okay. Then good that you are attending. In case you have any doubts, we can discuss on that. So week 8, question 8, Archita also told me about this question. So here you have bending taking place, and the cross section after bending becomes like this for your beam. And it is asked what kind of stress is being experienced at the top. So I think there's some issue with the answer key for this. The correct answer should be tensile, because even in lectures, sir has taught that you will have a kind of deformation of your cross section when you do the bending of beam. At the top, it will be something like this only, and it will be tensile. So I'll confirm with the mm, TA who is in charge of all of these answer keys. So he'll take this up. In case is
Okay,
any
sir.
clarification, we'll post it in the discussion forum only. But very likely the answer is tensile for this. I'll confirm with the TA in charge. The next question is okay, question 5. Let's go to week 5. Question 4, 6, 13, and 16. Question 4 is, which is the best suited technique for the whole field measurement of strain? So this is week 5, question 4, which is the best suited technique for the whole field measurement of strain. Hmm. So this we also discussed once in the week 4 doubt discussion session. So the correct answer for this will be DIC. The reason is, firstly, let's understand what is whole field measurement of strain. We know that strain gauge, which is what is usually used when you are doing tensile testing or any kind of loading, simple loading, it can only measure the strains in one direction, in one axial direction, right? So it's not a whole field measurement. It's just a one-dimensional measurement you are doing. But a different method like photoelasticity or digital image correlation, it can tell you the strains in any direction. It gives you a whole contour map of the strain. But the thing is, DIC will give you a map of the strains, while photoelasticity gives you a map of the stresses, and that too not uh, the exact values of stresses, but the sigma 1 minus sigma 3 whole square, sigma 1 minus sigma 3 modulus value, right? So
Sir, which will
basically,
give the contour value? DIC.
yeah. So have you seen any results of digital image correlation? I think sir has shown, right, in his lectures, that you can give a you will get a contour having different colors for different values of strains in different regions of your sample. And so based on that, it is easy to tell that what is the strain value at any point on your sample. And also it has the ability to give you the strain components of the strain at any point, which your strain gauge cannot give. It can only give you one component, but DIC can give you all two components if it's a 2D DIC, and three components if it's a 3D DIC. So that way it's the most convenient and accurate whole field measurement technique. Photoelasticity will give you values of stresses, but it is less convenient and it works in a smaller range of strain. DIC works over a very large range of strain. It will also work for elastic modulus. Like it will work fairly well for elastic modulus. It will also work for elastic regime, and it will also work for the plastic regime. While photoelasticity will not work when you enter plasticity. So that is why DIC is the most appropriate technique for when you are looking at strains and you want whole field measurement. Is it fine? Can or do you have any doubt?
Yes, sir.
That's fine. Next question is mm, question number 6. So since okay, let's go to question number 6. So question number 6 is about strain gauges. We have three strain gauges in a particular arrangement, and we need to know what is the value of epsilon xx. We have been given values of uh, epsilon a, epsilon b, and epsilon c. We want the value of epsilon xx, right? Let me just write down. And your epsilon b is in, sorry, epsilon a is in this direction. The measurement is in this direction. Let's, and this is x for us. This is y. This is epsilon c. Now we want to know epsilon xx. So for this, we have to do some transformation of the stress states. Sir has shown it in his video lecture. So I'll quickly go to that. So it's something like this actually. You have cos theta, sin theta. Let's say this is equal to A sin theta. So how do we do transformation when we are moving from one coordinate axis to another? Stress tensor transformation, I mean. So if your initial stress tensor was sigma and your new one is sigma dash, then it will be A transpose into sigma into A. and here you are rotating by an angle of theta. So same will be for strain. If strain tensor needs to be transformed to a new coordinate system which is at an angle theta, then you do A transpose epsilon into A. And sir has already solved this actually, and he has shown, if you just see what he got, like done the derivation, he has shown that sigma x will be equal to your epsilon A, and sigma y will be equal to epsilon C, and your tau xy will be a function of epsilon, sorry, should be epsilon B, epsilon A, epsilon B, and epsilon C. Here we have just been asked what is epsilon x, right? So it will be same as epsilon A. So the value will be 160 micron. Makes sense? And this is equal to 160 micron. If it is fine, I'll move to the next question.
Sir, we have to find a strain. What is we have written at the end? Tau xy.
Yeah, so normally, if you have any stress tensor, let's say you have a stress tensor like this, epsilon x, epsilon y, epsilon, and here, okay, I should not, sorry, tau means stress actually. I should write gamma here instead. Gamma, or let's say epsilon xy only. We are looking at strain components, so epsilon xy. So sir has shown a formula, and according to that, epsilon xy will be a function of the strain values you are getting at A, B, and C, and you are looking at components in particular directions, right? And what we are
Yes, yes.
doing is we are considering this coordinate system, which I am highlighting in blue. If this is the x, this is the y, then we look at what is the strain tensor for this coordinate system. And we'll get it something like this, which I've written on bottom right. Let me just write it like this. Mm, xy and epsilon yy. So this question was very simple because what was simply asked was this value epsilon xx, which is directly equal to epsilon a actually.
And sir, if we are allowed to find epsilon xy, then we have to find the function of epsilon a, epsilon b, and epsilon c. How we will do
Yeah.
that?
Okay. How we do that, no? So let me just go to the portion in the slides which has this. Hmm. Hmm. You can see my window. So this is week 5 content.
Sir, your window is not visible.
My now you can see.
No, sir.
Okay. Sorry, I think I didn't get her. Now I hope it will be visible.
Yes, sir, it is visible now.
So we go to strain measurement lecture. Lecture 15. I'll just write it down here. And here if we see, sir has done the derivation of how you can calculate gamma xy or epsilon xy. So it should be somewhere here. Hmm. Relations. Strain gauges. Okay, it's not in this. I think it's in this one. Hmm. So there are two kinds of arrangements that can be there. One is this one. I think it's called rosette. Yeah, three element rosette. And there is one which is delta one. So this is the delta rosette one, and there is rectangular rosette. So just look at this later on to understand the derivation for it. It's very simple. You just do stress transformation, stress tensor transformation. Sorry, strain tensor transformation. You find out what will be the, you assume that you have an initial starting strain tensor which is like this of which is for xy coordinate system. You shift it by theta, and once you shift by theta, for example, you had epsilon x dash, right, after shifting to theta. So that you find out the value of that by putting in the value of theta in your strain transformation equation. Let me just write it down. Maybe it will be more clear. Mhm. Do you understand the derivation for this, or should I
Sir,
explain?
if we are allowed to find it in the direction of B, then it
Hmm.
will be addition of purely B that is given around 100 plus we will find the angle derivation of C and A by putting theta as 45 in both case.
Yeah, yeah. So
So
for
then what is sir, what will
getting
be
the
the angle sir convention, angle sign convention? If we are doing clockwise, then we have to give positive or negative.
yeah. So the convention is that if you here you can see on the right, no, where my this maybe I'll highlight it. So here you can see that you are going theta anti-clockwise. So usually when we are doing coordinate system rotation, we almost always consider anti-clockwise rotation as positive and clockwise as negative. Based on that convention, we make our equations. For example, this rotation matrix is there, no, cos theta sin theta. This is based on this anti-clockwise as positive convention. So if you
Okay,
put
sure.
theta b equal to 45-degree in this strain tensor rotation equation, then the new value of sigma x dash that you get, this is sigma x dash actually, sorry, epsilon x dash that you get, that will be equal to epsilon b, right? Because you rotated from x to x dash by putting theta equal to 45-degree. So this will be epsilon b. It's shown here. And then if you just simplify, like use the other equations also, you will get the value of gamma xy based on these three strain values. From this, you can get what is the original strain tensor at that point.
Okay, sir.
Okay. Hmm. So it's just strain tensor rotation that you're doing. So there is also a similar question which you had asked. I think it's the last one, question 16. Uh, yeah, week 5, question 16. Where is it? This is a delta rosette based question. And here 16 is find out the value of gamma xy. right? So could you solve this one? Like, do you know what how you can solve this?
Sir, we have to find gamma xy in a diagram.
Hmm. For this kind of arrangement.
Sir, what will the theta we will take?
Uh, so let me solve this. Try to solve this. Then it will be clear to you how you can approach such problems. So for this,
Okay, sir.
sir has not directly told what will be the equations and the final values you will get. Let me just share my tablet screen again. Hmm. Yeah. So here you had three strain gauges at 120 degrees to each other. You know, let's call it epsilon A, epsilon B, epsilon C. And then now you have been told that you want to know that if this is your x direction and y direction, what is your value of gamma xy, right? So how we'll approach it is, if you have this as your strain tensor epsilon xx, epsilon xy, epsilon yx, epsilon yy, then you know that this if you want to rotate it by any angle. So let's say we try to find out epsilon b value. So this is at an angle 120-degree, right? So we want our new x. So if this is our x, this is our y direction. We want to rotate by 120-degree. So our new x, which we call as x dash, will be at 120-degree and parallel to your epsilon b direction. Okay, this is y dash. So epsilon x dash should give you the strain value you are measuring in your strain gauge B. So the component of strain along the direction B, the normal strain along like the direction B should be equal to epsilon x dash. So all we need to do is to do rotation of the strain tensor by 120-degree. What is the new value of epsilon x dash? What is the new value of the strain along x, which is epsilon x dash, and equate it to b, epsilon b. So let me do that quickly. So we already know what is the strain transformation equation. It is epsilon x dash equal to epsilon x cos square theta plus y sine square theta. You could understand the approach I told, plus gamma xy
Yes, sir.
sine theta cos theta. So what I'll do is I'll plug theta equal to 120-degree, and for this the value of epsilon x dash will that I'll get will be equal to epsilon b. So if I put theta equal to 120-degree epsilon, so we can directly write that epsilon b is equal to xx cos 120-degree is 1 by 2 minus 1 by 2, cos square will be 1 by 4 into 3 by 4 plus gamma xy equal to And here gamma xy is nothing but 2 times of your strain component. Gamma is the, what do you call it? Shear strain. I think, so gamma is equal to 2 times epsilon xy. I can't recall the exact name for gamma. And here you will have, as per this equation, you will have into sine 120 is root 3 by 2, cos is minus 1 by 2. Yeah. So this will be equal to epsilon xx plus 3 epsilon yy minus root 3 gamma xy by 4. Similarly, we'll do for epsilon c. For epsilon c, we'll have to have theta equal to how much? 240 degrees, right? And if we do the same thing, put theta equal to 240 degrees, we'll get epsilon xx. Just the value of cos theta, cos square and sine square will be same. Just the sign of uh, cos theta will sine of sine theta will be negative. So sine 240 will be minus of uh, root 3 by 2, right? So it should be something like this: epsilon x plus 3 epsilon yy. So instead of minus root 3, you will have plus root 3, because sine of 240 is equal to minus of root 3 by 2, and cos is also equal to minus of 1 by 2. This divided by 4. So you have epsilon b, epsilon c, and epsilon a. Now if we look at, so epsilon a will actually become equal to just epsilon, sorry, epsilon a will be just equal to epsilon x, because if you put theta equal to 0, only epsilon xx. X is the same as xx actually. Just for uh, doing it faster, I'm writing it this way. Also, this should be root 3 gamma xy. So we have been asked in question number 20. You asked question 20, right? No, no.
So
This
16.
is question 16. Yeah, gamma xy value. So what we can do for getting gamma xy, we can just subtract. If I do epsilon c minus epsilon b, I hope this approach you have understood, because rest of the things are just calculation. Then you get epsilon c minus epsilon b as this, right? And gamma xy will be equal to epsilon c minus epsilon b by 2 to root 3, which is equal to 68 plus 345 by 2 root 3 equal to mm, is coming as, okay, I'm getting a different answer. Mhm. Okay, there is this also 4 that we missed here. 2 root 3 by 4 actually. So this will be into 4 here. The 4 and the denominator, I just missed it. So I'll write it here into 4, and this will also become into 4. So this becomes equal to 476.9 megapascal. Okay. Hmm. In this way, you can find out all the, once you know gamma xy, you already know epsilon xx directly. You can know epsilon xy also by using these three equations. So this is your first equation. This is your third, theta equal to 240, and this is your second.
Okay, sir.
Based on these three equations. So we are just doing rotation of the strain tensor, and then according to which direction we want strain along, we know the value of strains along certain directions. We rotate our coordinate system to those directions and then see what will be the transformed strain tensor. After that is just some calculations you have to do. So that was question number 16. Next we have 13
13.
and 6. So I'll hurry a bit because we have more questions left. So question 13 and 6, right? Let's see question 6. Okay, 6 we have already done. So 13 only. 13 is what is the percentage reduction in area if diameter? Oh, let me go here. Question 13. It's related to tensile testing. You have been told what is initial value of diameter of your sample. So D initial is given, right? 25 mm. And final value has been told in the question to be 24.94 when it has failed. Mm. I hope my handwriting is okay, else I'll try to keep it better because I'll be uploading these notes later on. So I want it to be easy to understand.
Yes, sir.
Okay. So I'll try to make it a bit more clearer. So you have initial and final diameters given. We need to find what is the percentage of area reduction in area of cross section from start of test to the end of test. So this you can, so for this you know how to approach this or just your answer is not matching.
Sir, I haven't solved this question. I don't know how to solve this.
Okay. So what is given here is you are from a civil background, is it? Civil engineering?
Yes, sir.
Okay, you are doing like some a PhD program or master's program or something?
Sir, third semester.
Oh,
BTEC.
bachelor's program. Which which degree are you pursuing? Just I'm
Sir,
asking so that I'll know
BTEC,
how
sir.
much you
BTEC.
might.
BTEC.
Oh, you're doing bachelor's, no? So lots of things will be new for you.
Yes, sir.
So here I'll just give you some background of tensile testing. So what is happening is you have this probably dog bone kind of specimen. Here ASTM might be dog bone or cylindrical specimen. Let's say you have some specimen like this and it has been pulled in two directions, and then after pulling it, once it has failed, it will be slightly like this. There will be some necking, like some necking and some elongation. So it might have broken like this. It might be like this. So what happens is your length will increase. Sorry, this is a little difficult. Your length will increase. There will be some delta elongation, and also your cross section area will decrease. So this cross section area which you have here, it will slightly decrease delta area. Let me write. So we have to just find change in cross section area, which is equal to final area is pi d f square by 4 minus pi d I square by 4 divided by pi di minus the initial, right? Because you want percentage change. You understand this formula? And let me not do the calculation because this should be, I have already done it. The answer is correct. So this comes out if you put, just plug in the values. It will come out to be approximately 0.48 percentage. So your area
Sir, in the
will,
college they have shown this experiment, like the tensile strength of a nut bolt or a
yeah,
iron brace.
okay. Okay, they have shown it.
Sir, the area is not exactly circular, it's like zigzag area.
What kind of area?
Sir, zigzag area it is there.
Zigzag area. Oh, okay. I see. I see. That's why you are confused.
No,
Huh.
sir, that's a conceptual doubt. Yes, sir.
Huh. Huh. So, but actually, like, you can have any kind of sample. So I was saying na, that usually the most common ones are either a dog bone geometry, where you have something like this. The one I draw was more like dog bone geometry, or you have a cylindrical sample. So here your cross section will be like this. It will be something like this. Yeah. So this, it will be like this. So cross section will be a rectangle. And if you use a cylindrical sample, something like this. So you'll always have some gauge length where you will be observing your, where the maximum deformation will occur and your necking will occur. So this is your area of interest. And here your cross section will be circular. So since here you have been given diameter, so implicitly this means that you have a cylindrical cross section or cylindrical sample having a circular cross section. And the reason I am saying that it will be one of these two only is because as per ASTM stands, you know ASTM standards. So ASTM stands for American Standards for Testing of Materials. And this is something that industries use to compare between different materials. So there is a specific geometry which has been told by ASTM, and for tensile testing, it is either of dog bone or cylindrical. So you have to make your sample of this geometry only of particular dimensions and then do your testing. Then you can compare your properties among different materials. That's why it will be like this. Uh, is it clear? Should we go to the next question?
Yes, sir.
So I think then if you're in bachelor's, then many new things you'll be able to learn in this course because it's a very comprehensive course. So week 4, question 3, 7, 11 and 22. Week 4, question 3 is on photoelasticity. So let's go here. So Vishal, was this course recommended to you by someone? Someone told you
No,
that
sir.
you can
Sir,
do it?
it's in my syllabus, sir. Strength of material.
Okay, so for that, your like university course, you are all just doing this parallelly. Same syllabus
Yes,
is
sir.
there. Okay,
Sir, it is big
that's
bit large. I think it is. It comprises the mechanical engineering strength of material also.
Okay, I see. Week 4, question number 3, photoelasticity. You have a rectangular plate in which you are loading. Which you're loading, let's say in this direction, and when you do the loading, it is uniform, and you see uniform lines in your photoelasticity setup. So basically, uniform stress contours. But then you introduce a small hole in this, due to which there will be stress concentration, and your pattern of stress contour will change. So we call it fringes in photoelasticity. So that pattern will change. And it is asked, how will the new pattern be? So let's see what kind of stresses we can expect near that hole. If this is the enlarged hole, then actually sir has already shown that if you have this kind of loading and you have a small hole introduced, then around that hole, there just ahead of that hole, and so in the loading directions, you will have a high tensile stress, and around this region, just to the transverse, in the transverse direction of the loading, so in the transverse direction of the hole, you will have some compressive stress. It will not be high, but there will also be some compressive stresses, and because of this you will get some non-uniformity in your fringes, which will also be something like this only, the what I have drawn, just there will be some colors involved based on the value of the stresses. So the answer should be A, that it will be a flowery pattern. In the video lectures, sir has shown how exactly the pattern is. You can check there. So if it is fine, we'll go to the next question.
Yes, sir.
Hmm. In question 7, uh, it has been asked, you have been given a material of a certain geometry. It has been loaded in compression, and it is asked at what point stress tensor is 0. So this is based on a very straightforward concept that at all outward corners, the stress tensor will be 0. That is, all components of your tensor will become 0. So outward corners, all components of your stress tensor become 0. So material is not experiencing any stress at the corners.
So it will be black at the corner where it is no
Yes,
stress.
it'll be completely black. And in the diagram, you can see that all the outward corners, by the color itself you can see, but even if colors are not given, you should be able to identify that these are the outward corners, like A, C, D, F, G, I, J, L. So based on that, you can tell that there will be no stresses at those points.
Sir, anything more we can find with the color, like in point E or in point H?
E or H, is it? So actually, I was just mentioning, no, when I was talking about whole field measurement of strain. So photoelasticity does not give you strain value directly; it only gives stress value. So what it actually shows you is sigma 1 minus sigma 3, the whole square. So the fringes will be contours for this particular value in photoelasticity. So for example, in H, if you see, there is certain shade of blue you are seeing, right? So this shade of blue, if you have a legend which tells you which color corresponds to what stress values, it will tell you that at H you can expect a particular value of this sigma 1 minus sigma 3 whole square at H. So if you use the, for example, software which sir had told, which he has himself developed to be able to analyze these kinds of results, then you can tell what will exactly be the stresses at H and compare it with those at other points, for example, within the material. So that information you can get by using photoelasticity. You can get a sense of how the stress is varying at different points over your material. So those points where which have a certain color, like very red color. So reddish color usually tends to be high tensile stresses. Maybe bluish might be high compressive stresses. So those that information you can get from this.
Okay, sir.
Hmm. Okay, so let's next question is a question. If it's fine, we'll go to question 11.
Yes, sir.
Question 11 is also based on photoelasticity. You have four conditions, and here you have been asked what. So four different images are shown, and four different angles are there between the polarizer and the analyzer. You have been asked which one, which image corresponds to which arrangement of polarizer and analyzer. Um, okay. So the way you can approach this problem is by just understanding that what a polarizer is doing, that it is actually firstly just understand that both polarizer and analyzer, sir also mentioned once, are actually the same elements, just that they are situated at different places in your setup. So first comes the polarizer, then comes your sample, then comes the analyzer. They are both the same elements only, just that one is at one is before sample, one is after. And what they essentially do in very simple words is they filter out some part of your light wave. So there will be certain directions of oscillation which they will filter out. So you can understand that if you put a polarizer, the intensity of the light you get will reduce. Same will be for the analyzer. And also, if you change the orientation between the polarizer and analyzer, that will affect the final intensity you are getting. Because what you are doing is filtering out certain amount of light waves. So, mm, if you have understood that, then let's get to how the angles will affect the final amount of light that you get. If polarizer and analyzer are both aligned exactly parallel to each other, that is, there is no difference in the angles of polarization for both of them, then the light which is getting filtered by polarizer by the polarizer will go as it is through the analyzer. It will not get filtered again. But if the analyzer is at a high angle like 90-degree with respect to polarizer, then the light which came out of polarizer, it will again get filtered, because analyzer is at a different angle. It will also filter some portion of the light, and what you will get at the end will be much lesser, right? Because twice it has got filtered out. And in between 0 and 90-degree, there will be filtering, but it will be less. So you can say that at for the first situation where you do not have where both polarizer and analyzer are aligned in the same direction, you will have the highest intensity, and for the last situation where you have 90-degree angle, you will have the lowest intensity. So based on that, for orientation 4, I'll call it O4, you will have the least intensity, where you have a 90-degree angle between both of them. Do you have any doubts on this?
So the orientation 4 will be between A or D.
Between orientation 4,
Will be between A or D.
no, no, which is the darkest among A, B, and C and D, like according to
B,
you?
sir. B.
B, no? So 4 has 90-degree angle between polarizer and analyzer. So I told no that if it's 90-degree, it will filter out the most amount of light. So intensity will reduce the most. So finally, what you get will be quite dark compared to the other ones. So based on intensity, if you just try to put them in order, D has the highest, then A, then C, then B. So D should be for 0-degree angle and B should be for 90-degree angle.
Sir, if we are from orientation 1, if we are putting 90-degree polarizer,
Hmm.
it will
Yes.
filter the most light. Then
Ha. Yeah, yeah.
then how A at 90 degree will analyzer at 90 degree will analyze the light that polarizer has given. It should be same as orientation 4.
Same as orientation 4. Okay, so let's you asked about the first one, right? Orientation 1, where you have P equal to 90-degree, A is also
And
at
P equal to
90-degree,
90.
right?
Yes, sir.
So let's say that you have your light wave coming and it is oscillating in multiple directions, right? It's not polarized, it's oscillating in multiple directions. Your polarizer is at 90-degree, right? So it will only allow, let's say it's only allowing light which is coming at a 90-degree angle, right?
Yes, sir.
Those waves which are oscillating in a plane which is at 90-degree. So those waves will be able to pass through, right?
Yes, sir.
But now analyzer is also at 90-degree only. So it is aligned with the polarizer's angle, right? So it will also allow the same plane to go through directly without doing any further filtering,
Sir,
right?
polarizer filters out the light and analyzer just accept the light what has been given by polarizer.
No, so I told no both polarizer and analyzer do some polarizing of the light. When we say polarizing, what we mean is we restrict the planes on which the light can oscillate. So analyzer is also the same element, like it also has the same function. Just because you have two different polarizing units, you call one as polarizer, one as analyzer, and they have slightly different functions also. But they both are essentially doing the same things. Individually, they are both doing some polarizing of light only. So let me just draw it also. So what I'm explaining is in very simple way. So it's actually a bit more complicated. Some other things are also there in the actual setup. Let's say you have your polarizer like this. Let's say you have just a slit, okay? Your light might be coming like this, it might be coming like this, okay? On multiple planes it's moving. You have a slit like this, or let's say because polarization is 90-degree now, the angle is 90-degree. So let's this simple logic, if you understand, you will understand what is happening in polarization. So you have a slit and it's like this, okay? So similarly, you have your, let's say, sample kept here. Your photoelastic material is here. Then you have another slit, which is your analyzer. This is A. And here also it is polarizing at a particular angle. So this is what I meant. So when it goes through here, the light which is traveling here, it will only be traveling in this way, right? The perpendicular component will, the plane in the x, if this is x, this is y, and this is z, z is out of the plane. Maybe x, this is y. Yeah, if this is x, this is okay. I should this is x, this is y, this is z. So the xy plane, the oscillation which is happening on the xy plane, it will get removed completely due to this kind of polarizer, and you'll get something like this. And the analyzer will also allow it completely because it's also aligned in the same direction as polarizer. Now, does it make some sense to you?
Yes, sir.
So this will also allow it to go exactly like this. But instead of this, if you had this thing here, like this kind of analyzer at a different angle, so a polarizing element is nothing but a slit only. Just it's a very fine slit, like parallel fine slits, so that you get a much better information out of it. They make it very fine and parallel. So if this was the case, then you will not get anything, like almost zero intensity you will get if it was zero, right? It was if there was an angle of 90-degree between polarizer and analyzer. So you will not get almost no light you will be able to get. Actually, this got moved. Makes sense?
Yes, sir.
Okay, so just like try to understand based on this setup which I told. This is a very simplistic way of looking at it, but through this you can understand very easily. Then you can understand the more details of it later on. Okay, so
Sir,
this
question
was
22.
sorry, question.
22.
There
Next
is
question.
okay. This was question 11. Then we have 22. Determine the principal strain at this point. Okay. So yeah, let's go there. You could solve the other questions in this, and so for this particular section, could solve the other questions like value of strain at A, B, C, which is asked.
Yes, sir, but I'm getting the wrong answer in
Okay,
some
your
of the
answer is
question.
not matching. Sorry,
Yes, sir.
your answer is not matching. You know how to approach it.
Sir, I am a bit
Okay.
confused about the method approach.
Method of okay, let's discuss this. You have been given the displacement field in a body. So you have been given what is the displacement in the x direction, y direction, and z direction. It is something like this: x square plus y in the x direction, so I cap, plus 3 plus z j cap, plus x square plus 2y k cap. Okay, so at different points, how is the displacement of the point on straining? How that displacement is changing, that you can know by using this kind of a displacement field. How your body when it is strained will how different points will get displaced when your body is strained. That's what this tells. And this can, but this gives you just displacement values. What you are more interested in, which is more fundamental, not exactly fundamental but easier to work with, is your strain tensor value, epsilon ij. And sir, I think has already derived that your strain tensor will be something like this: dou u by dou x, dou u by dou y, dou u by dou z. These are the normal strain components, and the other ones will be half of dou u by dou y plus dou u dou v. Actually, there is this problem with notation here. Here in the question, and we are saying it as u equal to this, but when we were taught, it was actually, I'll open up that portion of lecture. Mhm. So sometimes the same variable is used in multiple different places. So you need to be careful what it means.
Okay, sir.
Here, I'll just see what variable sir was using. I'm a bit unsure. Hmm. So he was. He was just using UVW for displacements in x, y, and z direction, or I cap, j cap, and k cap. So instead of calling this as u, let's just call this as d, displacement displacement field, actually, not a vector, because you have variables here. And this you are calling as u, v, and w, the displacements in the x, y, and z direction at a point x, y, x comma y comma z. You'll have these displacements. So now you can write this strain tensor as dou u by dou y here and dou v by dou x. Similarly, this will be half of dou u by dou z plus dou w by dou x. So you see how we are writing this. Just
Yes, sir.
here we wrote dou u by dou z, because this is the shear strain we are looking at. So we want strain in x direction, but with change in z. And similarly, dou w by dou x, which kind of means strain in z direction, but as you are moving along x. Change in strain in z direction as you are moving along x. So if you use this formula,
Sir, by this formula, we'll find the A, B, C, D, E, F, and up to F value, no, sir?
so similarly you can populate the rest of the matrix. It's a symmetric matrix,
Sir, and
and
then about the
hmm,
major principal interest, we have to find the biggest and the smallest value difference.
yes, for the major. So from this you can know the stress strain tensor, all the values of A, B, C, A to F. Then you will have to find the characteristic equation for this, from which you will get the principal strain values, and then you'll have to use those. Here it is asked what is the principal strain value. So from that characteristic equation, you can just find the roots and that will be your answer.
Okay, sir. Understood.
Understood, no? So
Yes.
this is actually a bit lengthy process. You have to find the eigenvalues by forming that equation and seeing the roots, but it should give you the answer. Hmm. So next question. Okay, week 4 is done.
Sir, week 3, question 3.
Week 3, question 3. Okay. Hmm. So okay. Hmm. So we have a 2D loading here, and it is given that the Mohs circle is a point for this kind of loading. Your Mohs circle is a point which is at plus 150 units on normal stress axis. Hmm. So here you could understand what the Mohs circle will be. So what are the axes for constructing Mohs circle? On Y you have the shear stress, X you have the normal stress. And it's been told that your point is at 150 units on the normal stress axis. So let's just mark this as 150. And this is your Mohs circle. So here you just have a point. Oh. And we have been asked what will be the direction of maximum and minimum principal stresses. Hmm. So here, okay. So here, how you can understand what exactly is happening. We know what is the value of principal stress and how you can find principal stress, principal strain, and maximum shear stress using a Mohs
Yes, sir.
circle, right?
Yes, sir.
So from here you can see that there is just one point. So both your principal stress and both of your principal stresses will be the same,
Yes, sir.
right? And your tau will always be 0, right?
Yes, sir.
From this you can say that your loading is something like this 150, 150. It could be a biaxial kind of loading, right? And tau is 0. Yes, no shear stress is there. And now, even if you rotate this in any direction, for example, if you rotate it like this also by 45-degree, just by looking at the Mohs circle, you can tell mm, that still you'll have only normal stresses, which will have the same value. So this is kind of a hydrostatic stress state. Just that it is in 2D, not in 3D. So this makes sense.
Yes, sir.
Hmm. So you'll have at all in all directions you'll have the same normal stresses. The uniform kind of loading stress state. Yeah.
Sir, so
This
it
is
will be
fine.
in every angle degree, whether it is
In
222.5 or 45.
yes, at all angles it will be the same. You can
Okay, sir.
understand this just by looking at the Mohs circle also, because the what you how you can see this is as the circle has shrunk so much that now it's just at a point. So if even if you make your angles, which you usually use the Mohs circle for getting at a particular angle, what will be the stress and the shear stress and the normal stress, right? In a way, you are changing the your elements direction and finding the stresses for that element. But here, since it's a point, it will always show the same. sigma and tau values. Tau will be 0 only. This is fine.
Yes, sir.
Okay, so we'll proceed to next question. The next is question 8.
Sir, I've solved question 8, sir.
8 you have solved. Oh,
Yes.
so should we go to week 2 now?
Yes, sir.
Also, just since we were discussing this question on more circle being a point, you have also looked at three-dimensional stress states and Mohs circle for 3D stress states, right? So there, what we do is we make the Mohs circles for 2D for the 2D representations. So we'll make a Mohs circle for XY, for XZ, for YZ. So we'll have three Mohs circle to show the 3D stress state. But if you have a hydrostatic kind of loading, then you can understand that in all the three stress states, you will just have single points, right?
Yes, sir.
So there also your points will all be like your Mohs circle will collapse to a single point. So both in X, Y, X, Z, Y, Z, it will be the same point. The Mohs circle for all three will be the same point. That's what I mean. Mm. And there also, no matter which direction you look at, there will be no shear stresses, only normal stresses. Mm. Okay, so you have solved question 8, you are saying. So we'll go to week 2. Okay. In week 2, you asked question 16 and 21.
Yes, sir.
Mm. Okay, so 16 and 16, we have been given a stress tensor, and it is asked what is the value of sigma 1. Sigma 1 is your principal stress, the higher principal stress. So let's, okay. Week 2, question. This is related to Mohs circle only. We need to know the principal stress for a particular stress tensor that is known. So at your point 6 comma 10, if you put in the values of x and y, you will get sigma will be equal to. So you know how to approach this, Vishal?
Yes, sir. Yes, sir.
The answer is not matching, is it?
Yes, sir.
Okay, so let's just see. 3x square y. So that will be 1080 minus of x into y square and y cube 1000. And near most circle, you need to find sigma 1. So I think sigma 1 was the formula for principal stress. So this is equal to sigma x plus sigma y by 2 plus sigma y minus sigma x by 2 the whole square, or let's sigma x plus tau square, root of this, right? So
Yes,
this
sir.
will become 1040 plus minus. So we are looking at sigma only, so just plus will be fine. Sigma y minus sigma x by 2, 1800 plus tau square. Tau is minus 600, so 600 whole square. So square root of this, so this is equal to. What is the answer you were getting? Do you have it?
It's around 2000.
Okay. So this will come to approximately 1641 megapascal. So
Yes, sir.
this
It's
is
correct.
matching with the, I think some calculation maybe you missed somewhere.
Sir, question
This
21.
is fine, no? Question 21. Here also it's like this. So you know how to approach this question?
No, sir.
Okay. Here you have two rigid members which are glued at an angle. It has been told that the maximum shear stress and normal stresses they can withstand, those have been specified, and then you have to find out what is the maximum load, that axial load which it can endure. So question number 21, no? 21. Okay, let's just find out what are the maximum shear stress and normal stresses which can be applied. No, which it can endure until it fails. Okay. So question 21. So if you have, if we just look at the lower portion, there will be some normal stress sigma on it and some shear stress tau, and you are applying the axial load P. So sigma should not be more than 900 kPa, less than equal to 900 kPa, and tau is less than equal to 700 kilopascal. And we have to tell at what value of axial load it will fail by shear, that will tau, that is tau will become 700 kilopascal at which value of P. I think there are two ways to approach this. One is by just looking at the free body diagram for this. This angle is 30 degree with the horizontal, so this is 30 degree. Hmm. One way to approach is by just looking at the free body diagram. So you look at the components of the forces in the two directions. Mm. So if this is 30°, then this will be 60 degrees, right? And this will also be 60 degrees. If you find out what are the angle, it will come out something like this. And if we look in x direction, we balance forces in x direction, fx equal to 0, which will imply tau uh, sine 60, let's say sine 60° equal to sigma cos 60°. So tau equal to sigma into cos 60 is 1 by 2. So sigma by root 3. Then we can wait, I am trying to make a new page on this. It's not coming. Mhm. Yes, so now you have relation between tau and sigma. When you do sigma fy equal to 0, then you will have, this is week 2, right? So our time is almost up, but we'll just finish this, all of these, and then finish. So here you have tau cos 60 plus sigma sine 60° equal to P. So tau by 2 plus sigma root 3 by 2 equal to P. And you know here that for question 21, tau is given as tau is
700.
failing by shear, so 700. Here tau is sorry, tau is equal to 700. So this you can rewrite as, just substitute the value of tau sigma here. Sigma is equal to root 3
Okay,
into
sir, I
tau,
will do
right?
that.
Tau
Sir, I
plus,
will
you'll do it.
yes, sir, I will
Okay,
do it.
huh?
Sir, I
So
have
this
few
is one
questions
way.
from.
There is another way of doing it, which is the more formal way, because you have been here. You did not use the concept of strain tensor, right?
Yes,
You just tried to resolve the stresses. But another way is if you write the strain tensor for this, sorry, the stress tensor. We are dealing with loads here. So if you write the stress tensor, here you have your coordinate system. So this is method 2. Your coordinate system is like this, x and y. So your loading here is, and this is the more formal method, like proper method as per what concepts you have been taught. So here your loading is in y direction, right? So sigma x is 0, sigma y is equal to your p, let's say the stress which is associated with p, and your tau is 0. It's like a uniaxial loading, right? And what you have been asked is if you have an element which is at an angle of 30° with the horizontal. Okay. So if this is your element which is at 30° with horizontal, then what will be the value of sigma and tau for this? It makes sense.
yes, sir.
So for this, how you can approach this is 30°, then this is 60°. So mm, how you can approach this is, uh, you are rotating your this element by 60°. Rotation by 60°. And so this 0, 0 p after rotation will become some epsilon x dash, right? Epsilon y dash tau xy tau yx dash, right? So you rotate it by 60 degree and find out. And here, which element will you use? You want along x direction, right? The new x direction is of use to you. So you'll use epsilon x dash and tau xy dash. Those will give you the values of uh, normal and shear stress along the uh, cut that you have, which is at 30 degree with the horizontal, right?
Yes, sir.
So, and you know how to do rotation of your strain tensor
Sir, by
already.
multiplying transpose.
You multiply with that rotation matrix, right?
Okay, sir.
Hmm. So by this, if you do, you'll directly get epsilon. Here you have been asked what is the value of shear stress. So you'll directly get tau x, tau dash xy, and you can use that value. Hmm. Okay, so this is fine. We'll proceed.
Sir, I have few doubts from sir week 12, sir. How to
Week
approach, sir,
12.
few questions.
Week 1 is fine.
Yes, sir. I will do that. That one.
Okay, week 12. Okay, you can ask me.
Sir, in question 9, sir,
Hmm.
week 12.
Question 9. 6, 7, 8, 9. Okay.
Sir, I am confused between zone 1 and zone 3.
Zone 1 and zone 3. The beam is undergoing pure bending in which of the following, guys? Mhm. So in pure bending, you know what kind of fringe pattern you should see, right? So
So it will be
that's
sir,
again.
straight parallel,
Hmm.
parallel lines.
Parallel lines, right? In pure bending. But here you are seeing that because in between you have a change in the cross section area, there is a sharp corner there. So there is some change in pattern. But away from that, those portion where you have stress concentration, it is again becoming parallel lines.
Sir, in zone 1 and zone 3, they are both parallel lines.
Yeah. So you can say that it will be pure bending in those zones, 1 and 3. You know Saint Venant's principle, right? It tells that away from stress concentration or the loading points, it will
Sir, I
again,
think it is single correct answer.
it's a single correct one.
Sir, it is single or multi-correct. I am not sure.
Zone 1, zone 2, zone 3. But the correct answer should be 1 and 3. It might be single correct. I'm not sure. Let me just see. No, no, you can make multiple. The options have a square next to it, right? That means it has multiple options, correct? If it's circle, then you can only choose one.
So, sir, it will be zone 1 and zone 3, sure.
1 and 3 should. Yes.
Sir, in next question, sir, in 10, we are not given the dimensions.
Okay, in question 10, dimensions are not given. Dimensions, length of member is given.
Sir, it is at 2 meter or it is at 2 m in option B in the diagram.
Option B, small m, 2m, m, small s, small d. Let me just read the question. Actually, Archita had taken this, so I have not seen this question before. Sorry, Archita also has not taken because we were doing previous assignment questions in our doubt sessions. So let me just take a look. Hmm. Option A for option B for option C. Okay, so here you are saying dimensions are not given, right?
Yes, sir. Only area is
Uh,
given 100 millimeter square.
1000.
1000.
So one thing we know that the more the cross section is, the less is the tendency to buckle. Like more load will have to be, more compressive load will have to be applied for buckling of the column, right? So here
So
it is
you have to find
given.
the area as maximum
You
1000 millimeter
use this
square.
critical value for the cross section for different geometries because the moment of inertia will change, right? For each geometry. So because of that, the critical load for buckling will also change.
So the L effective will be L by 2 in this case.
L effective. No, I did not get. What are you asking?
So for buckling load, the length effective will be L by 2.
Effective length.
So in the formula of PCR, it is pi square into E into I minimum divided by L effective square.
I mean, okay, let me just check that formula. Actually, this portion Archita had taken. The third. This is the last lecture, right, of week
Sir,
12.
I have seen her lecture.
Ah,
I'm still in doubt.
okay. Let me just look at that formula. I'll then get back. So P critical is pi square. Hmm. So let's see what kind of end is this. One end is fixed. In the other end, we have it like it's more like a hinge in the other end. Okay. Pi square E by fixed. Okay, fixed pinned column. So please. What is the L effective you were telling? I'm not sure about it. Hmm.
Sir, in page number in lecture 39, sir has
Hmm.
given this diagram.
Lecture 39. Okay.
Page number
Hmm.
1043.
1043. Okay, let me go there. I'll share my screen. 1043.
43.
Okay. So this is on review of it. Okay. Okay, this is for the pendant. Equivalent column length that is used. Okay. So okay. Actually, I had not seen this lecture, so I was
Sir, it is
confused.
at point 7, no? In the
What
third one.
we are based on the boundary condition, sir is saying that you can change the value of equivalent length so that you can use the same formula for all kinds of boundary condition. So
Sir,
here
as
he
per the
has told
question.
that our case is the third one, right? One end is pinned, one end is fixed. So if I have a column of fixed pin, is clamped. Well, okay. Third one is 0.7 L, yes. But third one is the hinged one. I think
Yes, sir, yes.
fourth one is the one where you have it pinned. So in here also you have the hinged one only. So it should be zero point 0.7. Yeah, Le equal to 0.7. So this formula you can use
Sir, and the method approach, sir, for question 7.
for question
7.
7. Okay.
Method of approach.
Rectangular plate, small hole to far field stresses. Okay. Actually, here sir has directly told what will be the stress distribution, right? As a function of x and theta. You can see the formula he has written sigma theta theta equal to sigma xx into this.
So it will be maximum at 45. Theta at 45.
No, at 45 it will not be maximum. Just try to put theta equal to maybe minus of 90 degree or theta equal to 90 degree if you put what will you get? So you understand what this equation is telling you? That is more important. What is sigma theta theta here?
At theta angle, the hoop stress.
So sir has actually taught this in his lecture. So you are applying a particular stress which is 1 megapascal and sigma xx is your applied stress on the infinite plate.
So at theta 90, the cost to theta will be minus 1.
Cos 2 theta will be minus 1.
So it will be finally be 3 into sigma xx.
Uh, uh. So at an angle of 90 degree, which is the top surface and top surface is 90 degree, right? Anti-clockwise. So there you will have sigma equal to 3 times sigma xx, which is the highest tensile stress which it will experience.
So in 7 assignments, I have gotten more than 40% only. So this is the final assignment that I will be getting. If I want
Okay.
to pass, I have to get this 40 more than 40%. So I don't want to make any mistake.
Okay. 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 You have that kind of rule, is it?
Yes, sir. If I want to get certificate, I have to pass in at least 8 assignment. In
Okay.
7, I have
Okay.
passed.
Okay. So here the maximum hoop stress will be your 3 times sigma xx. And then it is asked what is the minimum hoop stress. Minimum will be the minimum value of sigma theta theta. And so that will be equal to um, cos 2 theta equal to 1. So it will be minus of sigma xx, right?
No, sir, cos theta is if it is cos theta is half, then it will be 0.
Hmm. Then it will be 0. But it can be less than that also, right?
At cos 60, it is so theta equal to 30 degree, it is 0.
The value of stress will be 0, normal stress. But if you have cos 2 theta equal to 1, then you will get the minimum value of sigma theta theta.
In negative.
Negative, uh, uh, it will be compressive stress.
So I have to put along with negative or only the magnitude in the minimum hoop stress.
Minimum hoop stress, you should put the negative magnitude. Okay, so it's the minimum hoop stress. It will be a negative value, yes.
Okay, sir.
It should be negative, yes.
So in question 17,
Hmm. Okay.
so in question 17, what will be the method of approach?
The compressive load, the structure is assembled as shown with a rectangular cross section. The what?
Sir, the moment of inertia in question 14, we have to do the minimum, no?
The moment of inertia for
Buckling.
question 14.
Yes, sir.
Yes, governing buckling behavior, so it will always be the minimum one. Yes.
Sir, at point B, there is axis given. So I don't think we have to take any one of the minimum. At
At
point B, there is axis given, dot line.
dotted line. Okay.
So I think the buckling will be in only one direction. I'm not sure.
No, no, it's not necessary. So, like if you have this, the buckling, see, it's like column. Okay, your BD, this is a truss, right? So your
Yes,
BD truss is, okay, you can consider it as a column, and you are applying a load from top, compressive load. So it can either buckle in the x direction or the y direction. If you're applying from z, or let's say you're applying from y, so it can either buckle along x or along z, right? So you will need
yes.
to see in along both axes which has the lowest moment of inertia that you will use, because it will have higher tendency to buckle along the direction which has lower moment of inertia.
Sir, point B is hinged or fixed.
Point B is connected to actually truss AC by a kind of a joint. So it can rotate about point B. It can rotate about point B. But here you need not really consider what kind of it's actually a joint which can rotate just like you have in trusses, right? In civil engineering, I think you study a lot of trusses. In materials, we do not study. I just have little bit of understanding. So it is pinned at B. The vertical member is pinned at B and D. It's written in the question, while the horizontal member is pinned at A and B. So pinning means that there can be relative angular rotation between the two,
Sir,
but
so
that
it is
point has to
pinned.
be fixed like to both. those 2 points, point in truss has to be fixed for that truss. Yeah. You got it? Like, what was your question? Hi, Vishal.
Sir, in question 17.
17. So what compressive load? The compressive load is N acting on the vertical member loaded as shown. So what is the compressive load that will act on the member N, on the vertical one? The vertical member is pinned at B and D while the horizontal is pinned at A and B with the load of 325 Newton acting at C. So here you have to critical compressive load. Here you have already been given what is the value of load applied at C, right? So you will have to make, you just need to know what will be the compressive load at B, which is experienced by the stress BD. So basically, what is the load in the negative y direction on the joint B? Body diagrams. Firstly, you can make for AC. See what will be the forces at point A, at point B. Then you make it for BD. For this, for each member you can make. At the joint also you can separately make. So if you make the free body diagram, do the moment balance, force balance, you will be able to get what is the force on the truss BD, okay, at the point B, and that will be a compressive force. That value will give you answer to question 17, and then you have to find out what can be the critical value, which will be based on the equation which sir told for buckling. So 17 is just based on doing the free body diagrams correctly and doing force and movement balance.
Sir, I will solve and send to both sir, to you and Archita. Please check what I have solved.
You have sent the solution.
No, sir, I will send tonight.
Okay, fine. Okay, you can send it. How will you send, by mail?
Yes, sir, mail.
Mm-hmm. Okay, we will take a look at it. So this is your like final assignment, so it's very important. You're saying, right?
Yes, sir.
Okay, then we'll take a look. Just mail it to us. That's all. Anything else?
No, sir.
Okay, so let's finish this session. Mhm. So thanks, Vishal, for asking the questions. I'm sure it will be helping many other students who are trying to solve the previous assignments.
Okay, sir.
So okay, let's wrap up this session. Uh, So this was the last session for the doubt discussion sessions taken by me and Archita. So now you'll be
Sir,
having the exam in
do
some
you have
time,
the
maybe.
solution of previous year assignment solution in PDF?
Solutions. Okay, those
In
are
PDF.
not present. Probably in the online video lectures, you can find solutions to many of the questions. Most of the questions, I guess, because we have split the previous year's questions between me and Archita, and we have taken it up in our discussion sessions. So the recordings should be helpful for that, I think.
Okay, sir.
Okay, thanks for attending. Thank you for being interactive. I'll be uploading the PDF of these notes in case you need to see it again. So all the best for your exams and
Thank you, sir.
revise it well. Okay, bye bye.
Bye.